Okay, so today we will talk about valuation rings and abstract non-singular curves. So we already we have already seen what is a non-singular curve, but we need to so we will enlarge that category. It's called abstract non-singular curve. So we'll see that we can define more abstractly. So, but before that, let's say something about very classical. There are some. See, when we study algebraic geometry, there are some guiding problems. So, what are they? Most of the in any area in mathematics, most guiding problems are classification problems. So, when I say classification problems, up to some equivalence. So, for example, this problem, which is the hardest problem in the classification problem in any category, that classify objects up to isomorphism. So, that is he in this case classify algebraic varieties up to isomorphism. So, like in topology, you want to classify topological space up to homeomorphism, which is extremely hard. You can similarly here it is very hard. It's next to impossible problem. I mean, it's very difficult. It's not so easy. But in certain cases, you can talk about, but they are very specific. So then you weaken the your equivalence relation. So what is this is so you cannot classify up to isomorphism. Then you ask classify algebraic varieties up to birational birational equivalence or birational isomorphism or birational equivalence. So that means on an open set they are isomorphic, but so they are almost isomorphic, but on an open set. And the third problem is that in a birational equivalence class, whether you have a non-singular object or not, or you classify first given a birational equivalence class, whether there exists a non-singular variety, or and further if there are, then can you classify them? So classify non-singular varieties within each birational class. Of course, if exist. If there are none, then the set is empty. Okay. So, as you see that these problems are very general. So, and they are very hard in general. I mean, it's a very it is not easy to answer any of these questions in general situation. But in the dimension 1, you have a very good answer to question number 2 and question number 3. So, all these problems are extremely hard. In general situation. But when dimension of the underlying variety is 1, the situation is simpler. It is simpler. you have some affirmative answer. Simple. So, for example, question number 2 and question number 3 has affirmative answer. And what is the answer? So, first of all, first of all, in each birational class, so the is that in each birational class, so answer is the following. In each birational class, so first of all, birational, you know, x is birational to y if the function fields are isomorphic, right? Kx is isomorphic to ky, right? These are all if and only statement. But so in each birational class, there exists a unique non-singular projective curve. So, this is the theorem. This is the main theorem in this section. So, further you can, I mean, you can make it more precise, like for example, suppose, so this is same as saying that suppose K is a field extension, or K over K is a field extension of dimension 1. So, that means that field extension with transience degree 1, right, because we are working over curve, transience degree 1. Then there exists a unique smooth, unique up to isomorphism, of course, unique smooth projective curve Ck such that sorry, such that Ck is such that the function field of Ck. So, if I so this K, so let me write like this, function field of Ck is isomorphic to K. And further, if you take two such function field K1 and K2, suppose K1 and K2 are two such field, so that is K1 over K and K2 over K, these are of transience degree 1. And if you have a map and there is a K homomorphism, K linear map from K1 to K2, or let us write K2 to K1. Then this induces a map of so K2 will correspond to smooth curve, projective curve Ck2. K1 will correspond to smooth projective curve Ck1. So, now this will be reversed. So, this induces a morphism of curve Ck1 and Ck1. So, this, if I write, this is phi star or phi, and then this is phi hash. And if you have a map of curves, you know the corresponding map of function field, that will be the phi itself. So, back and forth. So, in some sense, the function field of dimension 1 and non-singular projective curve, these two categories are equivalent. So, in some sense, category of smooth projective curves and category of the fields, function area of field over K, fields field extension over K of dimension 1, field extension over K of dimension 1 equivalent. Okay. So, this is the complete picture. But say, so in today's class, we will see that given a function field K, how to associate a smooth projective curve. Okay, that is the next. Okay, so first of all, if you take any so in the usual sense, I mean you take any non-singular curve, with function field K, and from now onward, whenever I write capital K, means that this K is a extension of little k of dimension 1. Okay. So, if I denote any y to be a non-singular curve with function field K, then if I consider this local ring, if I take point P in y, then OYP is a DVR. So, this is because Noetherian domain regular Noetherian domain of dimension 1 is a DVR. So, DVRs, like you know that DVRs are some kind of it's like they are nice objects, they are local rings, and they have some property, right, like the maximal ideal is a principal ideal domain. The maximal ideal is generated by a single element, and the ideals are also totally ordered. So, any two ideal if you take, then one is a subset of another. So, they are nice objects. So, this is for this this is a very important result. So, so reference I will give you can look at Atiyah MacDonald. Chapter 9. For a reference of this. Okay. So, now what is, so now let us call that Ck. So, new notation Ck is set of all DVRs of the K over K, I mean So, what does it mean? That means this is nothing but all those discrete valuation ring, so that it contains little k and it is inside in capital K. And the quotient field of R is, so that is the property of DVR, that quotient field of R is K. And also any element in K, either it is in R or its inverse is in R, any non-zero element. So, that is these are valuation rings. So, also it is a discrete valuation. So, you have a map to valuation map. So let CK be set of all such discrete valuation ring. So now the point is that if I take a curve like y, which is a non-singular curve, then with y I can associate a certain subset of CK. So I call it CY. And here I should say first that if I take 2 points P and Q in y, suppose y is any curve, non-singular curve, then I can talk about OYP and OYQ. Now, DVRs has some maximality property in the sense that the dominated, if they cannot be dominated by the other DVRs. So, that means this cannot happen, that if you cannot, they cannot contain, this cannot happen, that this kind of diagram is not true. If you have you take the maximal ideal here and if you intersect with this, so M, if I call the maximal ideal here MQ intersection OYP is MP. So, this is there, then this is called dominated. So, this kind of picture does not happen. So, in the sense that, so this is not true. So, this OYP and OYQ are distinct. So I write this statement. So, what does it mean? So, when y is a non-singular curve, OYPs are distinct. Okay. So, that means that given a curve y, I can associate let us call it CY. So, CY is nothing but the local rings P belongs to y, and they are all distinct. So, I can associate CY, but so this CY is set of all DVR. So, this is in CK. And now the point is that this will be a open subset, in the sense that the complement of CY in CK will be finite. So, that is a result that needs to be checked, but that is the fact. Okay, but before that, let me give a topology on this set CK. So, this is a fact that this is the complement CK minus, we will come to this again, right, that CK minus CY is finite. This is very crucial actually, and that is the starting point. So, this is basically of the fact that if you take any element in the function field, then the set of all DVRs which does not contain that element is finite. I mean that induces a topology. So let me state that result first, and then I define the topology on CK. So, lemma. This is a very important lemma. So, let X belongs to K. This is a commutative algebra lemma which is very important here. Then number of elements in R in CK such that X does not belongs to R. So, R is a discrete valuation ring. So, either you know that either X is in R or X inverse in R, that is the property of DVR. So, this is a finite set. Proof. proof I refer to the book, Hartson's book, chapter 1, section 6. And the idea is basically if you take some, so if x does not belongs to, if you take start with some such x does not belongs to R, so then you know that x inverse 1 by x belongs to R, but because this is not a unit in R, so 1 by x has to be in the maximal ideal, because set of all non-units forms a maximal ideal. It's a local ring. Then what you do, if you call this y, then you consider ky. Then y belongs to MR, so ky will be inside R, and this is k, right. Now you know that dVr has this property, dVr R is integrally closed. So what you take, the integral closure of ky in k, and if you call that B, then what you do, then you take the maximal ideal. So first of all, B will be inside R, that is clear, because R is integrally closed. So now you take the maximal ideal MB, if I call MB, which is MR intersection B, then this B comma, so this will be a this is a local ring. Now the point is that if you localize B of, if you localize MB, you get your R back. And then then after some, so this is how you, so this B is the, so you produce a affine curve. So if you take the corresponding, so this is a finitely generated K algebra, and then this is consider the corresponding affine curve. So that will that will give. So this is how the proof goes. I mean, I am not going to complete the proof, but it is a very much commutative algebra result. So I will leave it here. So this will say that there are finitely many R's such that yeah. So I'll refer to, you look at the, to complete the proof, you just look at this book, Hartson's chapter 1, section 6. Okay. Now but the point is, as a corollary, the important part is the corollary, the any dVr, so any dVr, so if you take a point in Y and if you take the local ring, that's a dVr. Now the point is that if the converse, you ask that if you take any dVr in Ck is isomorphic to, and this is the construction, this B will be the candidate, isomorphic to a local ring of a point non-singular. So if you start with any point in Ck or any dVr in Ck, then you can construct a curve abstractly such that local ring at one point is isomorphic to this Ck.